The objective of this work was to optimize an assist-as-needed exoskeleton controller in conjunction with a visual biofeedback video game, with the explicit goal of maximizing learning rates in a walking task for children with January bottom. In this study, we used the human-in-the-loop optimization approach with CMAES as our optimizer. This involved sampling various combinations of our tunable parameters and applying them to the biofeedback and exoskeleton system. From there, we collected the cost of each parameter set and used that to update our optimizer. We defined the cost to be the difference between the current score rate and 70%. And this was based on prior literature. This means that the closer the user is to 70%, the better the optimizer thinks that that parameter set was doing. Then, new parameter sets are sampled from the updated model, and the process is repeated again. The biofeedback game focused around instructing the user to perform a specific knee kinematic profile. The user-controlled avatar, the little red dinosaur, is controlled up and down by the knee flexion of the user, moving along the screen as they extend and flex their knee. The targets themselves, the little yellow boxes with birds, show the desired kinematic trajectory, and if they hit the box, they get a point. The size and position of these targets are adjusted by the optimizer during the experiment. The success rate is independently tracked for stance phase and swing phase, and the parameters are optimized independently for both. Simultaneously, the exoskeleton acts in an assist-as-needed fashion. This means if the difference between the measured knee angle and the target equilibrium angle is greater than a certain threshold, this being equivalent to the height of the targets in the video game, then a proportional assistance is applied. However, if that error is less than the specified tolerance, then no assistance is applied. This means that the better they do in the game, the less the exo assists them. Our results show that the optimizer is able to bring the pediatric subject to and maintain them at the targeted 70% success rate. Additionally, we see that the parameters required for this are non-constant over the course of the experiment, meaning that an online optimizer is needed to maintain the success rate as they improve. Additionally, we see kinematic improvements with a decrease in the stance phase hyperextension and the swing phase peak swing flexion approaching closer to the kinematic target of 65 degrees.